First of all, I would like to thank the organizers for giving me an opportunity to present my work at this wonderful conference. And this is the title of my talk. We have developed a numerical method to extract important degrees of freedom in quantum dynamics. So I will explain this method in this talk. And this work is done in collaboration with these people. And the main part of this talk is published in this paper. So this is the outline of my talk. First I talk about the motivation, and next we explain our newly developed numerical method. And we apply this method to light absorption spectrum and the photoexcited state in two-dimensional Mott insulators. And I find this, I don't have time to explain this. So from here. So spectroscopy is a powerful experimental tool. However, in strongly correlated electron systems, it is not easy to understand their physical property from the light absorption spectrum. For example, the light absorption spectrum for the two-dimensional Mott insulators is essentially different from the one-dimensional ones. This is a light absorption spectrum in the one-dimensional Mott insulators. The system size is 26. And the absorption spectrum consists of a few isolated peaks. And the spectrum shape is almost unchanged when the magnitude of Coulomb interaction is changed in the strong correlation region. And these features comes from the separation between spin and charge degrees of freedom. So in the two-dimensional Mott insulators, this is the absorption spectrum in the two-dimensional Mott insulators with various magnitude of Coulomb interactions. And the system size is 26. A band is formed in the 2D case. And the spectrum shape is strongly dependent on the magnitude of Coulomb interaction. So this strong dimensionality dependence is closely related to the difference in the spin-charge coupling between 1D and 2D Mott insulators. So the light absorption spectrum is an important stage to investigate the important problem of spin-charge coupling in Mott insulators. However, we have not yet succeeded in explaining these characteristic features in two-dimensional the absorption spectrum. So we apply our method to understand the spectrum, light absorption spectrum in the two-dimensional Mott insulators. So I explained the method of calculations. In the numerical solution of time-dependent Schrödinger equation is given by the linear combination of these basis states. And from the solution with discrete time with the time interval delta t, we can construct coefficient matrix. Coefficient matrix is NT by NB matrix defined by equation. NB is the dimension of the Hilbert space, and NT is the number of time steps. And row vector of coefficient matrix is the jth row of the coefficient matrix is the coefficient at time tj. This is a coefficient matrix. And singular value decomposition of coefficient matrix is given by the equation. Any matrices can be decomposed into this form. U and V are unitary matrices, and sigma is R by R diagonal matrix. R is the rank of C. And the diagonal elements are called singular values, and the singular values are sorted in the decreasing order. So using this decomposition, the solution is given by the linear combination of modes instead of the basis states. It's just a unitary transformation. However, this equation has a very interesting structure. The U gives the time dependence. And the important thing is here, the singular value is more precisely, the square of the singular value is the weight of the mode K. So the mode number is numbered in the order of importance. The phi 1, the mode 1 has the largest weight in the solution of the time-dependent Schrödinger equation. And if sigma k plus 1 is much smaller than sigma 1, then the solution is given by the linear combination of k important modes. The modes which have small weight can be neglected. And this is an important point. In most cases, the number of important modes is much smaller than the dimension of Hilbert space. In this case, the solution is given by the linear combination of far fewer important modes than the number of than the dimension of Hilbert space. So by this decomposition, important degrees of freedom for the dynamics are extracted. Okay, and as we will show, we use the effective Hamiltonian of 2D Hubbard model with 26 system size. In this case, the dimension of Hilbert space is 10 to the order of 10 to the 7th power, and we need at least 6,000 time steps. So C is a giant matrix. SVD of such giant matrix cannot be derived by conventional algorithms. So we adapted randomized SVD proposed by this paper. And I show the flow of RSVD in this slide, but we don't have a time. I don't have a time to explain in detail. But we want to emphasize this point. SVD provides practically rigorous SVD for the important modes, where the singular values are not negligible. So next we explain about model. We adapted two-dimensional Hubbard Hamiltonian. The Hamiltonian is given by two terms. K is the transfer term, describes the electron transfer between the nearest neighbor sites, and minus t is the transfer integral between the nearest neighbor sites. We use capital T to distinguish from time. So we use capital D for the transfer integral. And V is the Coulomb interaction term, and U is the on-site Coulomb repulsion energy. And to consider the light absorption spectrum, finite size effect is very serious. So we need to use the system size larger than or equal to 26. However, SVD of the coefficient matrix is impossible to perform with this size, even with using the RSVD method. So we adapt the effective Hamiltonian of the Hubbard model in the strong interaction case. So this Hamiltonian is very complicated, but to understand the physics, we have to explain several things. So this is the basis state, and arrows show spins, and empty site is called horon, and W occupied site is called doubleon. And horon and doubleon are the charge carriers in the Mott insulators. And the effective model of the Hubbard model is valid in the strong excitation case. We incorporate interactions through virtual excitations that change the number of horon-doubleon pairs perturbatively up to the second order of T divided by U. So the effective Hamiltonian for one photon excited state is given by this equation, very complicated. So PM is a projection onto the space with M Holland-Doublon pairs. So the Hilbert space of this effective Hamiltonian for one photon excited state consists of the basis states with one Holland-Doublon pair. The effective Hamiltonian for the ground state consists of the state 0 Holland-Doublon pair is given by this equation, and this is equivalent Heisenberg spin Hamiltonian. So the ground state of the effective Hamiltonian is the same as that of the Heisenberg Hamiltonian, and therefore the ground state has antiferromagnetic spin order. So I have to explain this effective Hamiltonian consists of various peaks, various terms. They are very complicated, but we have to explain two main parts. This part is only this part is proportional to T, and this part describes the transfer of holon or doublon to the nearest neighbor spin sites. And the other terms are proportional to T squared divided by U. And there are various terms, but the most important term is this term, Heisenberg spin-spin interaction. So we discuss physical property considering these two parts in the following. And here we check the validity of the effective Hamiltonian. We compare the optical conductivity calculated using original Hubbard Hamiltonian shown by blue line, and that calculated using effective Hamiltonian. We compare them with various magnitudes of Coulomb interaction. So as seen from these figures, in the strong correlation case, U divided by T is larger than T. The optical conductivity of the Hubbard Hamiltonian can be reproduced reasonably by the effective Hamiltonian. So the effective Hamiltonian is valid to describe optical conductivity or light absorption spectrum in this strong correlation region. So we numerically solve the time-dependent Schrödinger equation using this Hamiltonian, effective Hamiltonian, and the system size is 26, and we use the initial condition given by this equation. I don't have a time to explain the detail, but this dynamics is when the ground state is excited by ultra-short and weak light pulse and polarized along the x direction. And we solve the time-dependent Schrödinger equation numerically and construct coefficient matrix. And in this case, the coefficient matrix is constructed in the time range when light is off, and we adopt the large enough time range. Then, because of the uniqueness of the SVD, each of the SVD mode is identical to an energy eigenstate. SVD mode is the energy eigenstate in this case. And this is the SVD of the coefficient matrix. V gives the SV mode, so therefore V gives all the important energy eigenstates. U gives the time dependence. So Fourier transformation of U, we get energy eigenstates. And sigma gives the weight, so sigma gives the transition dipole moment. So from these data, we can calculate light absorption spectrum or optical conductivity. Here are the results. We compare the rigorous optical conductivity calculated by Lanczos method and optical conductivity calculated by RSVD method. The system size is 26, U divided T is 10, typical magnitudes of Coulomb interaction in motor insulators. And as seen from this figure, the rigorous optical conductivity and the RSVD result which considers 1,000 modes is almost distinguishable. So optical conductivity can be reproduced almost exactly by considering only 1,000 important energy eigenstates in this large dimension of Hilbert space. And as shown before, all the energy eigenstates that contribute to the optical conductivity are obtained by SVD. So this shows that important degrees of freedom for linear optical spectrum are extracted by SVD. And we want to emphasize that the number of important modes is far fewer than the dimension of the Hilbert space. So we apply this method to understand these characteristic features of the light absorption spectrum in the two-dimensional motor insulators. We calculate all the energy eigenstates that contribute to the spectrum and investigate their physical properties, considering these physical quantities. This is a spin correlation function, and the Fourier transformation of spin correlation function is a spin structure factor, and pi component shows the magnitude of antiferromagnetic spin order. In this case, all the states have the same eta 0. We use this quantity instead of pi component to show the quantity of the antiferromagnetic spin order. Then we also consider the charge correlation of holon and doublon defined by this equation. And minus xi r shows the doublon density at the site r when holon exists at the origin. And sigma c shows the standard deviation of doublon density. So we consider these quantities. And first we show the result in the strong correlation limit. T divided U is 0. In this case, the effective Hamiltonian is given by just only one term, and as explained before, this term describes the transfer of holon or doublon to the nearest neighbor size. And spin-spin interaction is not included in this case. This Hamiltonian just describes the transfer of holon and doublon. But this effective Hamiltonian is not a simple two-body Hamiltonian, because if holon is transferred, then this electron moves from here to here. So the spin state is changed by the transfer. Spin scattering occurs. So this spin scattering causes the spin charge coupling, as will be shown later. And this is the result. This is the light absorption spectrum when T divided U is 0 with the two-dimensional motor insulators. And we calculate all the energy eigenstates that contribute to the spectrum. And here we show the transition dipole moment from the ground state as a function of energy eigenstate for all the energy eigenstates. And seen from this picture, this state, please see the vertical axis, is about almost 100 times larger. The transition dipole moment is about 100 times larger than the other ones. This state has a dominant transition dipole moment. And this peak is due to excitation to this single peak. And this state has a much larger antiferromagnetic spin order than the other ones. and standard deviation of charge distribution is much larger. And this dominant transition dipole moment comes from this large antiferromagnetic order of this state, because the ground state also has the antiferromagnetic spin order. So we show the charge correlation function and spin correlation function for the energy eigenstate with dominant transition dipole moment. And this is a charge correlation function and spin correlation function of the state near the band edge. And as seen from this equation, this state has an antiferromagnetic spin order. Spin correlation changes plus minus plus minus. And this state, the spin correlation is very weak, and the charge correlation changes gradually. So these characteristics features can be understood as follows. If we assume two approximations, the form is wave function, it can be identified. First, the interaction between Hall and doubleon induced by the spin scattering is negligible. Because spin interaction is included, if Hall is transferred from here to here, the spin interaction energy is not changed. So this is not the bad. This is a reasonable assumption, and the transfer of Holon or doubleon induces the phase shift. If we expand the energy eigenstate, this basis states, if we compare the coefficient, the transferred one has a phase shift compared with this one, coefficient, compare the coefficient. And as well known, in the Bloch state, the phase shift of the moment of Holon is added. But not only the moment of Holons, the phase shift is added from the surrounding spin state. And this is valid, this is rigorous when there is only one Holon, but we assume that there is a Holon and doubleon. If I assume this, the energy eigenstate can be written by this equation. Q is the momentum Holon and doubleon, and S shows the spin state. And this is a spin wave function where there is a Holon at N site and doubleon at M site. We don't show the detail, but the energy eigenstate of this state is given by this equation. And this result agrees consistent with the numerical result by SVD. And okay, so first we see this energy eigenstate. There are few Holon-doubleon momentum that are compatible with periodic boundary condition. If phase shift due to spin is 0, the light absorption spectrum consists of a few isolated peaks, just like the case of one-dimensional motor insulators. Since there are a large number of spin degrees of freedom, and the shift is added, thank you. A band is formed. And so this shows the reason why in the two-dimensional case is a band is formed. And we don't have a time, so we skip charge correlation function. And spin structure. If the Holon is transferred along this trajectory, the spin state is changed, and large number of parallel spin pair is generated around here. So free translation motion destroys antiferromagnetic spin order. So in the free doubleon Holon states, antiferromagnetic spin order is very weak. But in the case of this case, this specific Holon doubleon moment, if this spin wave function have a finite weight, then the weight of this spin function is 0. So only in this case, the chain of this superposition is cut, and therefore antiferromagnetic spin order is not destroyed in this case. So we have to have. So this is the reason why only this state has a large transition dipole moment. And okay, so I have to hurry up. Next, we show the result when the reasonable magnitude of Coulomb interaction, and this is the result of in this case. As seen from this picture, the energy eigenstate can be classified into two categories. The energy eigenstate is circled by this line, and the other ones. And the other ones are free Holland-Doublon states as described before, and these energy eigenstates are localized Holland-Doublon states. And localized Holland-Doublon states has a much larger antiferromagnetic spin order. This is a charge correlation function and spin correlation function of a localized Holland-Doublon states. The charge is localized around this equation, around here, and we can see the spin antiferromagnetic spin correlation. So we explain this mechanism. So if Holon moves here to here, parallel spin pair is generated, and antiferromagnetic spin order is destroyed. However, the effective Hamiltonian have a spin flip term. So if spin flip occurs at this distance, the antiferromagnetic spin order is preserved when distance, Holland-Doublon distance is here. So Holland-Doublon interaction induces the interaction, and there are several minimums. And these states are localized at these distances. So this is the bound state of spin order, spin origin. It's not a bound state due to direct Coulomb interaction. So if we compare the spectrum when the Holland-Doublon bound state induced by the direct Coulomb interaction, in this case, Holland-Doublon bound state has a dominant transition dipole moment. And in this case, it's not so big, large, and this is consistent with the experimental data obtained by Professor Okamoto's group. So I have used too much time. So I finish by showing the conclusion of my talk. Thank you for your attention.